Hi, everybody. In this video, we're going to actually talk about our last topic that's in our notes set right now. And it's going to be 18.4.2, mathematical modeling with exponential and logarithmic functions. So mathematical modeling is just some terms that we use to say, hey, we've created this model or this equation or this function to model the situation that's in this word problem. So can models absolutely be wrong and predict wrong things, or even model past trends in an incorrect way? Yes. And so we're always looking, scientists, mathematicians, educators, I mean, pick any, like if you're in the business department, we're always looking for different types of ways that we can model different scenarios based off of just data that we're collecting. And I mean, no matter what field you're in, even if you're in the natural horsemanship program, you can absolutely collect data and then look at the trend that's occurring in your scatter plot and say, what type of model is this? Is this linear? Is it exponential? Is it quadratic? Is it logarithmic? Is it something else? Maybe it's a power function. And you can come up with your model, and then based off your model, you have such power in that because you can make predictions, you can look at past trends, and it's really powerful to be able to do that. So in this topic, we actually have all of the math tools we need in order to do this topic. And so this topic is really focusing on looking at different word problems and different scenarios. And then they give us a mathematical model or a mathematical equation, and we get to solve for a different piece of it, or we get to plug information into that equation. Some of them are a little bit more intense in the process, but I'm going to walk through these problems with you. If you wanted to, you could totally pause this video right now. Well, after we get through the blanks, you have to stay with me until we get through the blanks. But then once we get to the word problems, you could totally try to just pause the video and see if you could do the word problems on your own, and then come back and watch the video and see how you did on those word problems. All right, so let's look at the first ones. So here it talks about some of the scenarios we're going to be dealing with. So it talks about the alkalinity and acidity of a substance, the Richter scale, decibel measures. Some of these we've actually already looked at in some previous examples. So some of them are going to be review, and some of them we're going to do a little bit different thing with. All right, so the Richter scale context. Let's look at the Richter scale. A Richter scale is a logarithmic function, logarithmic function, that is used to measure the magnitude of earthquakes. The magnitude of an earthquake is related to how much energy is released by the quake. Instruments called seismographs detect movement in the earth. The smallest movement, just like the smallest decibel from that other example, the intensity level was measured with I sub 0. Well, that's going to be what happens here, except instead of I sub 0, it's going to be A sub 0, because we're talking about amplitude. So we look, the smallest movement that can be detected shows on a seismograph as a wave with amplitude A sub 0. So again, A sub 0 is the smallest detectable kind of movement we're going to see. So true or false, are our tectonic plates moving all the time, and that there's tiny movements all the time on Earth? The answer to that is true. So there are tiny movements happening all the time, but sometimes we don't recognize them, right? So they wouldn't even be a sub-zero because we're not even detecting them. They don't even register on the Richter scale. But they're occurring because our tectonic plates are in constant motion. But we're not recognizing it, or we're not noticing it ourselves. So it doesn't even register. So it would even be below a sub-zero on that. So the sub-zero again is the first thing that's gonna be detected. All right. So A is the measure of the amplitude of the earthquake wave. A sub 0 is the amplitude of the smallest detectable wave. or standard wave. From this, you can find R. The Richter scale measure is of the magnitude of the earthquake using the formula. So here, and again, I kind of said that funny, but it's from this you can find R, which is the Richter scale measure of the magnitude of the earthquake using the following formula, which is R equals log of A over A sub 0. I hope that looks familiar. That should look familiar to the decibel equation that we were looking at the other day, where we had I over I sub 0. So then we've got this note. The intensity of an earthquake will typically measure between 2 and 10 on the Richter scale. Any earthquakes registering below 5 are fairly minor. That doesn't mean it's minor for the people encountering them. It's kind of scary. We get them in Dillon every once in a while, and it shakes the house. And like our chandelier a while back was like shaking or like swaying because I shouldn't even say chandelier, it was just our light fixture hanging over our dining room table, which is not a chandelier. But anyway, it was swaying because we had an earthquake that hit close to our area, but it wasn't too bad. It just was weird. It's kind of shaking around. And it was minor, but it was still odd. But anyway, it says they may shake the ground a bit, but are seldom strong enough to cause much damage. True, that's exactly what happened. Earthquakes with a Richter scale rating of between 5 and 7.9 are much more severe, and any quake above an 8 is likely to cause massive damage. And at the time of doing this video recording and writing these notes, the highest one that's ever been recorded so far was a 9.5 in 1960, and that was occurring in Chile. An earthquake is measured, and here's one of our problems we're going to work on. An earthquake is measured with an amplitude that is 392 times as great as A sub 0. So we've got a wave, and its amplitude is measuring 392 times that of A sub 0. So what is the magnitude of this earthquake using the Richter scale to the nearest 10th? So again, we're using the Richter scale, so we're going to use our formula of R equals, come back up here, and it's log of A over A sub 0. And they told us what A is. A, our amplitude, is equal to 392 times that of A sub 0. This is what our A equals. So we're going to plug that in for right up here. And we're going to have log of 392 times A sub 0 all over A sub 0. And that equals R. Well, just like in our decibel example the other day, the A sub 0s, well, the I sub 0s in that one canceled out. So the A sub 0s are going to cancel out here. And then you need to take log of 392. So put that in your calculator. We're going to round to the nearest 10th, which is going to be 2.5932, and that keeps going, which is going to be 2.6. And that is our answer, 2.6. And there's not a label to put on here. It's our amplitude. So it's 2.6. And notice a difference of 1 point on the Richter scale equates to a 10-fold difference, right? Because we're talking about a log function, which is a base 10. And so if we're changing that, even by a single point on the Richter scale, that is a 10-fold, or the power of 10, it is a 10-fold difference in the amplitude. So thinking about like a wave that would normally be like this, and then you have like your central part of the wave, and then you're measuring what the amplitude is here, right? From here to here. Well, 10 times that is going to be like way up here doing 10 times that wave. So even a small difference, I mean, it's going to come like way down here. What we think is, oh, it's only a point difference. It's a big difference when we're talking about the waves. All right. Oh, we've got one more blank fill in. This means that an earthquake that measures 3.6 on the Richter scale has, well, duh, 10 times, we already said it, tenfold. So 10 times the amplitude of one that measures 2.6. So you're putting in 10 times there. All right, let's try another one. So an earthquake monitoring station measures the amplitude of the waves during a recent tremor. It measured the waves as being 100,000 times as a sub-zero, the smallest detectable wave. How high did the earthquake measure on the Richter scale? So again, what did they give us? Which part is this? That's what you should be asking yourself. And they gave us A again, and we're asked to find R. So R is our unknown. And we are going to be plugging in. So it's going to be R equals log of 100,000 A sub 0 divided by A sub 0. The A sub zeros cancel out. So then you're doing log of 100,000. So I got a little anxious with my comma there. I'll cross that off. Log of 100,000. So again, you're asking yourself, 10 to what power is going to give you 100,000, or you can put it in your calculator and do 100,000, hit the log button, and you should be getting out 5. 5 for registering on the Richter scale. All right, now we're looking at 3. 3 is one of those problems I'm hoping you're going to rewatch and watch and watch again, because it's going to take a little bit. And this one, I'm going to tell you right now, it's like one of the problems on your study guide. I think it might be like one of the last problems on your study guide for your final. It is. So this problem is very, very similar to your number 31 on the study guide. Again, as of this video being recorded, it is number 31 on your study guide. So just you should write that down. Like number 31 on the study guide. Similar to it, similar process. All right, so we have a hot water pump. It has a noise rating of 50 decibels. One dishwasher, however, has a noise rating of 62 decibels. The dishwasher noise is how many times or how many more times more intense than the hot water pump noise. And recall, here's our decibel formula. So read that again and tell me, what do we know this time and what are we solving for? So read that again and tell me what you think. So pause the video and I want you to see if you can at least tell me, what are we solving for? What did they give us? All right, hopefully you've paused the video and you figured that out. So we have two different things. We've got the hot water pump and we've got the dishwasher. So over here on this side, I'm gonna do the hot water pump. We're gonna talk about that. And then we've got the dishwasher on this side. So I'm gonna do those two. And it says the hot water pump has a noise rating of 50 decibels. Well, where's that gonna go in? That goes in for D. And it says one dishwasher, however, has a noise rating of 62 decibels. Where's that gonna go? That's also gonna go in for D. Then it says the dishwasher noise is how many more times more intense than the hot water pump noise. So we this time are looking for I in this example. And then not only are we looking for I, but then at the very end, we're gonna compare them. And we're going to do some division there to look at the ratio to know how many times more intense is the dishwasher compared to the hot water pump noise. So by the end of it, what we're going to be doing is we're going to be comparing the intensity of which one's higher, the dishwasher, compared to the intensity of the hot water pump is what we're going to be doing at the end, once we even find the I's to begin with. So this is a little bit more of an involved problem. All right, so let's look at the first one. The hot water pump we know is 50, so it's gonna be 50 equals 10 times the log of I over I sub 0, which we don't know. And again, what I want you to do is think about the fact that we're solving for our argument. So when we're solving for our argument, what's our process? Like, how do we get that argument all by itself? And even remembering from yesterday's or from the previous video that you're looking at, you're having to convert it into exponential form to get the argument by itself. So before we even do that though, what I want you to do is divide both sides by 10 to get rid of this 10. So let's do that first, and then we're going to get the log of the argument all by itself on one side of the equal sign. So now we've got 5 equals the log of I over I sub 0. Now I would like you to convert that into exponential form. And it's going to be 10, because we've got 10 here, right? 10 to the 5th equals this. So 10 to the 5th equals I over I sub 0. So don't worry about the fact that we have 2 i's in here. What we're going to do is we're still going to solve for I. So how do we get I all by itself? We're going to multiply both sides by I sub 0. And what I know now is that the intensity of our hot water is going to be 10 to the 5th. And I'm going to leave it as 10 to the 5th. 10 to the 5th times I sub 0. So that's what I know. Now let's go look at the dishwasher. So the dishwasher, what it said, 62 decibels? Yes. So 62 decibels equals 10 times the log of, and I'm just going to go ahead and put my notation on there of intensity of the dishwasher. So I just put dW down there, over I sub 0. Follow the same process, divide both sides by 10. We're going to get 6.2 equals log of the intensity of the dishwasher over the initial intensity. And now we're going to convert it into exponential form. So 10 to the 6.2 is going to equal our argument. 10 to the 6.2 is going to equal our argument of I dW, I sub dW over I sub 0. Now we want I dW all by itself, so multiply both sides by I sub 0. And we're going to get 10 to the 6.2 times I sub 0 equals the intensity of the dishwasher. All right, so now we have those two. Now remember, our final question in this is how many times more intense is the dishwasher compared to the hot water? So now we're going to do intensity of dishwasher over intensity of hot water, and we're going to figure out what that is. So intensity, so that's going to equal, and I'm going to put it down here. We've got 10 to the 6.2 times I sub 0 divided by 10 to the 5th times I sub 0. So now let's solve. We can cross some things out. I sub 0s are going to go away. Now use your rules of exponents here, and we're going to have 10 to the 1.2, right? Because we're just subtracting this off, minus 5. And so that should be 10 to the 1.2. And then go ahead and tell me what that's going to be, and that should be 15.85. So what that means, we're going to write a statement now. Therefore, this little symbol, by the way, means therefore. Therefore, the dishwasher noise is about 15.85 times more intense than the hot water pump noise. All right, I know it's a lot. You might have to go back and rewatch that one. But you should check it out, see if you can do that one on your own. All right, let's look at number 4. So number 4, it says if lime juice has a pH of 1.7, so there's a piece that they gave us, pH of 1.7, what is the concentration of the hydrogen ions in moles per liter in the lime juice to the nearest hundredth? Okay, So let's plug in the 1.7 equals negative log. And again, we're looking for H3O positive here. So I'm just going to put an X. I'm just doing shorthand notation so that I know that X is going to equal H3O positive here. So first thing, let's get rid of that negative. We're going to divide both sides by -1. So then we're going to have negative 1.7 equals log of X. Again, we're looking for the argument. When we're looking for the argument, what's our process? What is our process? We convert. So it's going to be 10 to the negative 1.7 equals X. 10 to the negative 1.7 equals X. So then we are approximating that to be 0.02 concentration of H3O positive ions for that one. And that was in moles per liter, by the way. So that was our also, that could have been your label as well. All right, let's check out another one. Number 5, how long will it take to the nearest whole year for the month, or not the month, for the money to double if it is invested at 10% compounded monthly? Recall the compounding interest formula below, where P is the principal, A is the amount, R is the annual rate, as a decimal, M is the number of compounding periods per year, and T is the number of years. So how long will it take? Well, which variable are we looking for? How long? We're looking for T, we're looking for time. So let's fill in our variables off to the side. Let's figure out what these each are. R, M, and T. All right, so we already know T's are unknown. It says, how long will it take to the nearest whole year for the money to double if it's invested at 10% compounded monthly? Well, how much money was invested to begin with? We actually don't know. It's an amount. Well, let's figure out, because that's not very helpful when we have another unknown already. Well, what are we finding out? We're finding out how long is it going to take for my initial money to double, which means for the amount of money, how can we express that in terms of P? We're going to say 2 times P. I want you to think about that. Why would we do 2P? Because we are figuring out how long will it take for our money that we invest. How long is it going to take for that money to double? Are we even still going to be alive for when it doubles? Well, let's find out. So P and 2P. R is, what was the rate? We've got this 10%, which you need to convert into a decimal. So it's going to be 0.1 or 0.1 is what I like to write in here. So 0.1, and then it's compounded monthly. So how many times is that per year? That's going to be 12. So now we're ready to plug this in. But something cool is going to happen with our P's. Don't you worry. We're going to have 1 plus 0.1 all over 12 raised to the 12t. I'm hoping that you see right now we're going to have a variable in our exponent, and I'm hoping you're thinking about what are we going to ultimately have to do at the end of this to solve for it. So I want you to be thinking about that. All right, so we're going to have, let's first get rid of this p. We're going to divide both sides by p, and those cancel out. Awesome, we got rid of one of our variables. 2 equals, and now what I want you to do in your calculator, I want you to take 0.1, divide it by 12, then add 1 to it. So take 0.1, divide it by 12, add 1 to it, and you should be getting, I don't know, it looks like 1.0083 repeating, 1.0083 repeating, and it's still being raised to the 12t. So now what I would like for you to do is think about what do we have to do in order to bring this down to solve for my exponent. And I'm hoping you're saying take the log of both sides, Liz, and that would be correct. So we would say log of 2, and then I'm going to bring this down because we're going to be able to take the log of both sides, right? So we're going to have log of 1.0083 with that 3 repeating, 12t. Because I took the log of both sides, I can use that property that says I can pull that down. So then I'm going to have log of 2 equals 12t log, and that's going to be multiplied there, log of 1.0083 repeating. And I want to solve for t. So how do I undo all this multiplication that's in between t and these other numbers? You divide. So we're going to divide both sides by 12 times log of 1.0083 repeating. And we're going to put that over here. 12 times log of 1.0083 repeating. So here's what I would do. I would, in my calculator, I would probably do 2 and then hit the log button, excuse me, and then I would hit divided by. And then in my calculator, I've got these little parentheses buttons right here and here. So I would do log of 2 and I would hit divided by, and I would do beginning parentheses, and I would do 12 times 1.0083, and I would punch in as many 3's that will work in there. And then I would hit the log button, and then I would hit equals. And then so far what would be showing up would be the equals to just what my denominator is. And you have to hit equals again. So I'm going to try that and make sure that process even works that I told you in that calculator. So I'm going to do 2, and then I'm going to hit the log button, and then I'm going to hit divided by, and then I'm going to hit beginning parentheses. Oh, I think I forgot to tell you close parentheses. So I'm going to hit beginning parentheses, and then I'm going to hit 12 times, and then 1.00833333, as many 3's will fit. And then I'm going to hit the log button. So I'm taking the log of that number. And then in my little, I don't know, screen, it's showing me 0.0036. I'm going to close parentheses, and then I'm going to hit equals. And then you should be getting 6.9603. 6.9603 on that one. You are also more than welcome to always break it down even further. So let's say that was too many buttons to push in there. You can always do 1.0083333333, as many will fit in your screen. Hit the log button, multiply it then by 12. And then on that one, I end up getting like, so I would still have log of 2. And then you could write down 0.04324949. Do not round though. Do not round that one because you don't want a rounding error at the end. So then I would put in my calculator 2, hit the log button, and then you get, like for me, I get that 0.3, what does that say? 0.1, and then it just keeps going. So that's what I got for log of 2. And then I would divide it by that decimal that I just noted. So 0.043244949, hit equals, and I'm still gonna get the same thing. Of t is approximately equal to 6.960313 ... So how long does it take for my money to double? Approximately 7 years was my answer. And again, you were supposed to round to that. It says to the nearest whole year up here. So that's why I rounded to the nearest whole year, because it told us to. Let's try another one. Number 6, another population one. Oh yeah. According to the US Census Bureau, the world population in 2011 was 6.9 billion people, and it would grow about 76 million. That is crazy, 76 million people. It would grow about 76 million during the year. That is, it would increase by about 1.1%. So what we get there is that it says, then we make a conclusion statement. Thus, the world population P in billions of people could be estimated for T years after 2011 by the following formula. So now we are supposed to estimate the population in the year 2050 after 39 years have passed to the nearest 100 million. So here we go. To the nearest 100 million. So they give us this time of 39. So guess what? It says estimate the population. So this time we're just looking for P. P is going to equal 6.9 times 1.011. We're raising it to the 39th power. So put that in your calculator. So 1.011 to the 39th, hit enter or equals, then multiply that by 6.9, and you should be getting 10.6 billion, because that's what our formula gives us. But guess what? 10.6 billion, you can also call that 10.6 100 million. And the reason for that is because our 10th, like where it says a 10th of a billion here. So here we have a 10th of a billion. And so it's already, so 10.6 is already to the nearest 100 million. I don't know if that made sense, but that is why you can leave it like that and why they both mean the same thing. Because again, I'm just going to reiterate that a 10th of a billion is 100 million, right? It's 100 million, trust me. Okay, here we go. That was that one. That one's not so bad. The next one. So here we go. Estimate by what year the population will be double what it was in 2011. So we've got our formula up here. And it says estimate by what year the population will be double what it was in 2011. So I want you to pause the video and like just think about how we're going to set that up using our equation from up above. And I want you to think about how our population, what was it? In 2011, I'm missing you. Where are you? Oh, it's right here. So our population in 2011 was about 6.9 billion. And then we're asking for like, when is it going to double? So 2P is going to give us 13.8 for that. So what that means is that we can plug 13.8 in for our P on this time. The P, so it's going to be P equals 6.9, 1.011, and it's raised to, I think it was just the T, right? Yeah, to the T. And so what that means is that for our P, we can plug in 13.8 right here. And that's going to equal 6.9 times 1.011 raised to the T power. So what I would first like you to do is divide both sides both by 6.9. Do not subtract. Some people like to subtract here. Don't subtract. You're asking yourself what operation is occurring between 6.9 and 1.011 to the T, and it's multiplication. So how do you undo that? You divide. So make sure you're dividing there. Let me see. So here you should be getting 2 equals, oh, having problems with my pens. 1.011 to the T for this. And then I've had some students here, by the way, too, say, well, I mean, if you wanted to, what you could do is just say, if we know, I just want to pause. This is why I was pausing a moment ago. So we could have also set it up like this. 2P equals whatever our population was times 1.011 raised to the T. We could have set it up like that too. Then we divide both sides by P, and then we would get 2 equals 1.011 raised to the T. So I've had some students set it up like that, and they wanted to know if that was okay. Totally fine. You can set it up like that, because look, we're right back. We're at the same spot right now. All right, so how do we bring this t down? We're going to take the log of both sides. So we're going to have log of 2 equals t times the log of 1.011. Again, taking the log of both sides allows me to bring that exponent down. Now you're ready to divide both sides by the log of 1.011. Sorry, it's kind of messy in here. Log of 1.011. And then t, once you do that, so you should go ahead and divide that. Tell me what you get. You should be getting approximately 63.359. And so it says estimate by what year. So I'm not even done with this problem yet. So estimate by what year it's going to be there. Well, you can't, on this one, you can't just truncate. You can't just say 63. Like you don't want to round it down, because after 63 years, is it going to be double? No, it's not until 63 years and almost 4 months that it's going to be double. So, and it just asked for us to do the years. So we're going to say that this is 64 years. That's still not my answer yet. Now it's saying what year? What year will the population be doubled? And you're going to take 2011 and add 64 to it. And so you should be getting 2075. So by year 2075, the population will have doubled. And again, that's based off of that model, which could be correct, and it could maybe not be correct. But anyway, it's by year 2075. So there's your final answer right there. All right, last example. So a particular bacterial colony doubles its population every 15 hours. A scientist running an experiment is starting with 100 bacterial cells. She expects the number of cells to be given by the formula right here, where t is the number of hours since the experiment started. So after how many hours, so there it is, that's what we're looking for, would the scientist expect to have 300 bacterial cells? So we're going to plug 300 in for C, and it says give your answer to the nearest hour. So we're going to do 300 equals 100 times 2 to the t over 15. You should pause the video and see if you can do this one on your own. We've done enough practice on this. I want you to pause it, try it out on your own, and then check your work. So we're going to first divide both sides by 100. Then we're going to get 3 equals 2 to the t over 15th power. Again, how are we going to solve for that t in the exponent? You should be taking the log of both sides, which allows us to bring that exponent down. So we're going to have log of 3. I'm going to go ahead and bring it down in this step, knowing I'm taking the log of both sides, equals t over 15 times the log of 2. I'm going to come over here where I have a little bit more room. Then I'm going to divide both sides by log of 2. So far I've got log of 3 over log of 2. I've had some students at this point just cross off the logs, and then they're like, cross off the logs and it's 3 over 2. No, don't do that. Don't do that. That would be like you saying 10 to the 3rd over 10 squared. Oh, I'm just going to cross off the 10s and my answer is 3 over 2. That is not true. So don't be tempted to do that. The log of 3 is some other number, right? All right, so then we've got equals t over 15. Again, we're still trying to solve for t. So we're going to multiply both sides by 15. So then we've got 15 times the log of 3 divided by the log of 2 equals t. So what I want you to do, and if I was just using this very simple basic calculator, I would be doing the log of 3. So I would do 3, hit the log button, then I would divide it by the log of 2, which then I would hit, so I'd divide it by 2 and then hit the log button, hit enter or equals, and then I would multiply it by 15 to get my answer. So then it's going to be t equals, or approximately 23.77, and that keeps going. And then again, we were asked to the nearest hour. So the nearest hour is going to be approximately 24 hours for that. And we are done. Way to go, you guys. I'm proud of you for hanging in there and finishing your notes and getting your last example done and just kind of finishing strong on that note. So if you guys have any questions, please be sure to ask me in class and I'd be happy to go over any of these again. Thanks for tuning in.